Continuing with this series of videos, watching the the lectures of Professor Lewin at MIT from 2000 and whatever, 7 or something, and so this one on diffraction gradients and such. See if we can get through this in one piece, but who knows.
We discussed the interference patterns due to two coherent light sources. Today I will expand on this by exploring many light sources. Suppose instead of having two slits through which I allow the light to go, I have...
Thank you, YouTube. Oh, free book offer. I don't want a book offer. What is it doing? Why is it doing this? It's not playing the frickin' video. There's no... What do you mean an error occurred? This is rubbish. Oh, come on. What?
So last time,
I hate YouTube.
we discussed the interference patterns due to two coherent light sources.
It's been doing this kind of stuff a lot to me lately. So it's like, I guess YouTube doesn't like me either.
Today I will expand on this by exploring many light sources. Suppose instead of having two slits through which I allow the light to go...
Alright, so let's understand. So he teaches the subject by first going to the two-slit experiment, then the multi-slit experiment, and then he'll go back to the single-slit. And I would argue there's a reason for that, which is keep you confused.
I have many. I have n, capital N. And let the separation between two adjacent ones be d. And so plane parallel waves come in, and each one of these light sources is going to be a Huygens source.
Alright, so, see, these are all little details, but they're sort of important. So in the two-slit, D was the thickness of the little impediment. And now D, okay, is the distance between the impediments. So we're back now to single-slit math.
We're going to produce spherical waves. And so now we can ask ourselves the same question that we did before, and that is, look at a long distance far away at certain angle theta, where will we see maxima and where will we see minima? And then we can put up here a screen at a distance L, and we will call this x equals 0, and then we can even ask the question, where exactly on that screen will we see these maxima? You will have constructive interference.
Okay, so now we have the 0 is back. So in the single slit, there's a 1 where the 0 is. Okay, there is no 0. So now he's kept the double slit 0 for the n, but he's changed the distance to the distance between, the opening of the slits. And the Huygens source isn't creating two waves per opening, it just creates one wave somehow. So I'm just saying this is how it's sort of engineered to get their correct answer.
Exactly the same situation that we had with the double slit interference pattern, when the sine of theta of n equals n lambda divided by d. And if you're dealing with very small angles theta, you should all remember that the sine of an angle is the same as the angle itself, provided that you work in radians. So for small angles, you can always use this approximation. Remember that it is in radians, and that's only a small angle approximation. And so the conclusion then is, if we work in radians for now, that theta of n for the maxima is then an n lambda divided by d, n being 0 right here, n being 1 right here, n being 2 right there. And if you want to express that in terms of a linear displacement from 0, then x of n, again for small angles, is L times that number. So you will say, well, big deal. It's the same result that we had for the double slit interferometer.
So it's fairly, so he called it the double slit interferometer, slip of the tongue or whatever. I mean, it's hardly an interferometer, a double slit or a gradient. But anyway, yeah, so the math is kind of simple, right? You're just talking about, okay, the angle is going to be proportional or directly related to the wavelength and the width of the slit. Those are the two things that are going to dictate the angle. And Once you have the angle, it's just a matter of, you know, it's kind of a simple over distance, the fact the angle grows at a certain rate.
We had exactly the same equation, there was no difference. And D now is the separation between two sources here. It is obvious.
So a completely different D variable. So you can't get much more different, right? I mean, the width of the impediment versus the width of the slit they're very different D's. So I mean, he just trivializes it like it's not a difference. It's a huge difference.
Is that it is the same, because if these two are constructively interfering, then these two will too, and these two will too, and these two will too. So all of them will. So it's not too surprising that you get exactly the same result. But now comes the big surprise. We haven't discussed yet the issue where the locations are, where light plus light gives darkness. We haven't discussed the destructive interference. And to derive that properly is very tricky. In fact, if you take 803, you will see a perfect derivation. But I will give you the results. What is not so intuitive, that if you have n sources, that between two major maxima, that means between this maximum at n equals 0 and a maximum at n equals 1, there are now n, capital N, minus 1 minima. And minima means complete destructive interference. So if capital N is 2, which we did last time, 2 minus 1 is 1. Exactly, that was correct. We had only 1, 0 in between the two maxima. But that's not the case anymore when capital N is much larger than 2. And so let me now make you a sketch whereby I plot the intensity of the light as a function of angle theta. And this is the intensity. So that's in watts per square meter. Remember, that's the Poynting vector. And let this be 0. And let the angle theta 1 be here. And for small angles then, that's lambda divided by d. And here you have theta 2, which is 2 lambda divided by d, and so on. I take the small angle approximation. So this angle is now in radians. What you're going to see now is the following intensity as a function of theta. You see here a peak, and you're going to see here a peak, and you're going to see here one, and so on. And the same, of course, is true on the other side. And here in between, you're going to see now n minus 1 locations whereby you have total destructive interference.
And you may have the same thing in the double slit pattern, but they kind of just gloss over it, because the double slit pattern essentially has two patterns superimposed on when revealed at its best relationship. So if you find the best numbers, you can maximize the effect of this fact that there's an envelope with which the pattern exists in. And so the more slits you add, the more the envelope becomes more and more obvious. And it's not a single slit envelope, as they state in the double slit experiment. It has the same proportions, but I'm saying there's no reason to think that there's any necessary relationship between that appearance.
And the same is the case here. And this can be huge, n can be a few hundred. So you have many, many locations where you have 100% destructive interference. Now this point, this first location where we hit the 0, that now is at the position lambda divided by d divided by capital N. And I will call that angle from the maximum to that 0, from this maximum to this 0, I will call that angle for now delta theta. Because that delta theta is a measure for the width of the line. Here is it maximum, here it is 0. And so that angle delta theta, in terms of radians, is lambda divided by d times n, which then is approximately theta 1 divided by n, because theta 1 itself is lambda divided by d.
And the other curious fact is, when you do the experiment, these the more you narrow the slit, the more the more lines, the more round, perfectly round the light becomes, imitating the round laser. And that you can see it in images also. So when you use this diffraction gradient to, just viewing stuff through it, you'll see that it creates images in the wrong location. And it separates them by color, by frequency. So it works like a prism and moves the image at the same time to these certain locations. So it's essentially the entire image. Since the laser beam's not being confined, it hits a whole bunch of lines. There's no slit blocking it, so to speak. It's essentially just reproducing an image of the laser beam at the different locations, and that gives you some insight into what the double slit's doing, in the sense that the light goes through. It's reproducing the image of the light in the different locations.
And so you see that it is n times smaller than this distance. And so if n is large, these lines become extremely narrow. And that's the big difference between two-slit interference and multiple-slit interference.
Right, and so there's another thing to think about is, in the old days when they put the light through a small aperture before they sent it to the double-slit experiment, they were essentially bowing the light. I mean, they were diverging it. So it had a higher intensity and then lower intensity. And when they shot that light through the slits, they would likely get a more gradual pattern on the wall, because they're sending light in that's more gradual. And with the regular laser beams, when you just shoot one directly straight through, there's more consistency in the intensity of the light, and that's why the pattern looks so bar-like. It's because you're getting an image of exactly what goes through the slit, which is there's no gradient in the intensity. So I'm just using this as a logical argument to understand that what they're saying is composing this pattern isn't what's composing it. It is an image that's just being it's being sent to each one of those angles.
And the larger n is, the higher these peaks will be. The height of these peaks, the intensity here, is proportional to n squared. You may say, gee, why is it not linearly proportional to n? Well, that's easy to see. Suppose I increase capital N, the number of sources, by a factor of 3. Then the electric field vector, where there are maxima, is 3 times larger. But if the electric field vector is 3 times larger, the pointing vector is 9 times larger. So you get 9 times more light. Now you may say, gee, that's a violation of the conservation of energy. 3 times more sources, 9 times more light. How can that be? Well, you overlook then that if you make n go up by a factor of 3, that the lines get narrower by a factor of 3 because of this n here. And so they get higher by a factor of 9, they get narrower by a factor of 3, and so you gain a factor of 3 in light. Of course you gain a factor of 3. If you have 3 times more sources, you get 3 times more light.
So none of that happens. It's the simple point is that the light is reflecting at longer, wider distances. So like in a single slit, the blobs get bigger and further apart. In the case of where you've now created a very, very thin slit, it now only reflects at certain angles, and that's it, very precisely. And so all the light goes to the one location, and no light, very little light goes to all the little humps in between. So, but yeah, there's nothing to do with pointing vectors.
See, there's no violation of the conservation of energy here. And I want to demonstrate this to you using our red laser, which we have used before. And I will use what we call a grating. A grating is a plate which is specially prepared, a transparent plate, which has grooves in it. And the one that I will use has 2,500 grooves, we call them lines, per inch. That means the separation D between two adjacent grooves, in my case, is about 2.16 microns. A micron is 10 to the minus 6 meters.
It would be interesting to know what the difference between these grating and a polarizing film, what the number of line differences, because the polarizing film is also using lines, and so I've never really seen that expressed, because it does get sort of interesting, because when you start putting more and more grooves in, you're coming closer and closer to duplicating what a polarizing film is doing. And I just haven't seen that anywhere, a comparison of where they are on the some sort of linear chart of number of grooves.
And the wavelength that I'm going to use is our red laser, which is about 6.3 times 10 to the minus 7 meters. And I'm going to put the whole thing there. I'm going to make you see it there at a distance L, which is about 10 meters.
So the obviously point I would make is that as you narrow the grooves, as things are closer and closer together, there can be fewer and fewer electrons in between things. So that's why there's less and less angles, and the electrons would be under more and more pressure. So the closer two surfaces are, the more confused the electrons are going to be, because they don't like each other and they're being confined. And so obviously they're going to be moving or be in a tension that's going to be higher than they would be if the slit was wider.
And so this allows me now to calculate where the zero order will fall, where the first order and where the second order will fall. Recall, when n is 0, we call that zero order. So this is
their obsession, is merely calculating where you'll, some sort of proportions about what distances you'll see things at, when, in my opinion, the thing to be concentrated on is the actual production of the effect, what's causing it. And, but they don't really have a great answer besides saying the word Huygens, which isn't a great answer.
Is zero order. When n is 1, we call that first order, and when n is 2, we call that second order. And you have, of course, the first order also on this side, and the second order also on this side. Everything that you have here, you have to also think of it as being on the other side. So I can predict now where the zero order will be. When n is 0, that is 0 degrees. That's immediately obvious. I use that equation. If n is 0, the zero order is always right at the center, provided that all these sources are in phase. And they will be in phase because I use plane waves. So Huygens will tell you that they're going to oscillate exactly at the same time. They produce the same frequency, they produce the same wavelengths, and they're all in phase with each other.
And the obvious point is the laser beam's a tiny thing. Going through the tiny thing, the projector is projecting on a screen. Obviously that tiny thing, all that light goes right straight through. There's some light that goes straight through and it's going to hit the target right in the middle. So there's no real obstructions in a sense, because all the light's going to go right through the center.
So there will be a maximum at theta 1 equals 0. And then there will be a maximum which I calculated to be at 3.55 degrees. I calculated that from this equation, and then theta 2 will be at a roughly 7.1 degrees. If you want to know...
Twice. It's always just the same angle multiplied, indicating some sort of repetitive event. Like you hit 1 electron, you go 3 degrees. You hit 2 electrons, you go 7 degrees. You hit 3 electrons, you go... sort of works as a possible explanation.
Know how wide the width of this peak is going to be, then you have to know how many lines of my grating I will be using. Well, my grating is like so. Here I have these lines, not unlike the grating that you have in your optics kit. There are 2,500 of those lines per inch, and my laser beam is roughly 2 millimeters in size. So this is about 2 millimeters. And that tells me then that I cover about 200 lines. And if I have 200 lines, I can now calculate how wide that line is going to be, because this factor of n enters into it here. And if I express that in terms of that angle delta theta, then the angle delta theta, going back here, so delta theta is then the 3.55 degrees divided by 200. And that's an extremely small angle. That angle is approximately...
Right, so the beam is basically going to be the laser beam, and then whatever divergence there is built into the laser beam. So you're not going to get away from the divergence of the laser beam, but obviously when you divide a number like 3.5 by 200, or yes, you're getting a very insignificant almost size change in the laser beam size. So it's only a tiny spread of the laser beam, and the more lines you add, the smaller and smaller that change becomes, and you're basically stuck with the width of the laser.
1 arc minute, which is 60 times smaller than 1 degree. And if you want to translate that in terms of how wide that spot will be, if I see it on the screen 10 meters away from me, and if you want to call that delta x, then you would naively predict that delta x is something like 3 millimeters. And the reason why I say naively, because you will not see that it is 3 millimeters. It will be extremely narrow, but it will be more than 3 millimeters, because the limiting factor is always the divergence of my laser beam. And
so he's just pointing out that all you're seeing is the laser beam. So the gradient can't do much to change the size of the laser beam except cause more divergence. And it can't cause more divergence because there aren't enough electrons. Once you're getting small enough lines, it's not going to matter anymore.
So the divergence of my laser beam is more than 1 arc minute. And so I don't get down to the 1 arc minute narrow beam. I'm not too far away from it though. So this is what I want to show you first. I will turn on the laser first. And then make it very dark, because we do need darkness, or this has to come off. So that would obviously... Oh, I turned off the wrong laser, but I turned on the wrong laser, but that's okay. That's a second demonstration, which I do with a green laser. This is the one that I need. This is the red laser. It will come on very quickly. There it is. Tom, if you could turn that off, maybe that will help, although everyone can see it, but it would help. So you see here very clearly, the zero order is right in the middle. This one, so theta is 0, and this theta 1 is my 3.5 degrees. This is also 3.5 degrees. This is the 7.1 degrees, and so on. And so you see this whole pattern of interference.
Obviously, those first 3 ones are much brighter than the ones later, because clearly you can't even see those. So these 3 almost look the same intensity, but this is all just camera effects and whatnot. But clearly it drops off rather significantly.
As a result of multiple slits. And so these are grooves in a piece of plastics. And notice how small they are, how narrow they are compared with the double slit interference. So they don't have that theoretical minimum with this 1/n, but they approach that.
Notice that they're basically images of the laser beam at different locations. That's what they basically are, and that's what the gradient does in real life. If you hold one up to your eye, you'll see images in different locations. And so it's just taking whatever comes in and making copies of it at the different locations. And if you understand that that's what it's doing when there's multiple slits, that's probably what it's doing when there's a double slit. That it's just taking whatever light goes in and theoretically sending it to all the locations by, each photon has a probability of going to, obviously it has more probable to go to the center location than to the other fringe ones, but it will go to one of those locations, and those are the locations it goes to, and it's just an image of what goes through the slits. That's why it's a bar shape. It's because it's an image of what goes through the slit.
And the reason why they are not that narrow is because the divergence of the laser beam itself is larger than that 1 arc minute that I calculated. And so you can never beat that, of course. We did this experiment with red light, but keep in mind that if I take red light, here is a maximum at 0 order, here is a maximum, provided that this lambda is lambda for red, here is a maximum, provided that this is the lambda for red. But if I have white light, then of course I deal with other colors. And if I have blue light in my white light, it will also have a maximum here, that's non-negotiable, but it has its first order maximum here because the wavelength is shorter, and it will have its second order maximum here. This will be the same distance. And so when you do this with white light, you're going to see always at 0 order white light, because all the colors have their maximum at 0 order. But at first and second and higher orders, the colors walk at their own pace, so to speak. And then the smaller the wavelength is, the closer it will be to the 0 order, and then the spacings between first.
Yeah, so it gets a little bit confusing. But like I said, when you're viewing the world through your eye at it, what you'll see is the light coming from a sharp angle will be doing the same thing as light coming straight through. So objects on your periphery will actually be sending those things on angles. And so one of those will go to you. So you'll see an image, you'll see the object over there, but you'll see a copy of the object over there. So you'll see multiple views of the world based on the location of those spots and the fact that each thing is creating the same pattern as all the light goes through. So you'll see one image and then another image and another image. But to do that, you have to turn the grating. If you're trying to look at the thing straight ahead, you have to turn it to see the ones at different locations. and each one at a different location will have its will be prismatically, the light will be prismatically spread. And he'll probably point that out, that that's they can use that to analyze the spectra of emissions and absorptions of light and chemistry.
And second, will also be smaller than in the case of the long wavelength, in this case red. And this is something that I also want to demonstrate to you. It is not so easy to get a very strong, powerful source of white light. I'm using for this a reflection grating. You can also use gratings in reflection. You take metal, and then the grooves are made on the metal, and you get a reflection which we will have there on the wall. This reflection grating has a spacing which is 4 times smaller than the one we have here. It's only 2.5 microns.
So that would, it's 4 times smaller, which is pretty small, which are pretty, it's only 50, then he's saying, lines. So this is where it could get interesting, you know, because it's obviously reflections are so much different than something going through 2 slits. So, you know, I think that should inspire some further looking into this. But reflections fits what I'm arguing, is that with reflections you can obviously understand that the image is just being reflected to the different locations, and it's not being reflected to the ones where there's no surface to hit to reflect. So obviously the peaks and valleys, when the light hits, can only reflect off the side of the mountains, so to speak. Can't reflect off the surfaces that aren't in the right angle.
And so the angle theta 1 will not be 3.5 degrees, but it will be 4 times larger. The main purpose why I want to show you this is I use white light, that the 0 order is white. And then we will see also, of course, the first and the second order, if we have good eyes, because the whole thing is not so...
Yeah, so it makes perfectly good sense that the center where the light went straight would be white. Yes, but it's not going to get spread, because the photons went through without hitting anything to refract them.
So very bright. Make sure that I have my light, flashlight. There it is. I don't even have to tell you what the 0 order is, do I? The 0 order is the same location for all the colors. So clearly, this is the 0 order. You may be...
Obviously there's not much symmetry there, so the angle must not be right. I mean, the second order is much smaller on the left side than the right side, kind of thing.
Surprised that the 0 order is so broad. Why isn't it very narrow? Because there are so many lines per inch. The reason is, of course, that no matter how many lines per inch you have, your spectrum will never be narrower than the actual size of the light source itself. And so the reason why this is as big as it is because the light source is big.
Exactly the point. It's just an image of the light source. That's all it is. There's the light source is projected an image of itself, and the rest are just images spread. They want to be round little circles, but they can't be because they've been spread, because the light at different frequency changes the angle. And so they'd be little white dots, and they're just images of what goes through the however you want to look at it, whatever gets reflected, the light that gets reflected. It's just an image of the reflected light, the light that hits the right surface.
So all the colors fall at the same location at the 0 order. That's why you see white light. Here is the first order spectrum. Notice that the red is farther away from the 0 order than the blue. Here is the first order on the other side. Again, the red is further away from the 0 order than the blue, and you can even see here the second order. And again, the red is further away than the blue.
It's the third order where it really drops off in intensity for some reason. So he doesn't say anything about that, but clearly the first and second order are much brighter than the third order.
I now have a red laser, which is pointing in exactly the same direction as the white light. And so I make a prediction now that the 0 order of the red laser must fall in here, that the first order of the red laser must fall here in the red, that the first order of the red laser must fall here in the red, and it must fall here in the red of the second order. So I'm going to turn on the laser. Be a little patient. There it is, exactly as predicted. Notice that the red laser always falls at the location where the white light has the red in its spectrum.
Right, and notice that they're not mixing in any way, and it's not doing anything bizarre. The photons aren't waving in some different way. There's not more interference or any of that kind of stuff. It's just a separate interference pattern, exactly what it's supposed to do, like the two photons don't even interact at all.
And that's what you expect, of course. And the zero order is right here. There's actually a much better way that I can make you see all this, and that is if I ask you, which I think I'm going to do now, to use your grating. Just hold it for a second before you get your own gratings out. Our equations that we have derived so far only hold if we look very far away. These angles of theta are only true if you go very far away. For reasons that we discussed last time, we can, however, do something very clever. We can use a lens. And if we have a lens, we can bring the image very close without disturbing the angles. If this is a grating, there's a number of sources that I have, and so the light comes in this direction, and if I put here a lens, and this is the screen, the focal point of the lens, then if the angle theta, for which I would have expected in this direction my first order maximum, and here of course my zero order maximum, then the lens will not change that angle. We never discussed lenses, so it may not be so obvious to you. But the lens will always maintain the integrity of angles. So the angle theta that we derived here is the correct angle, but of course in terms of x, that is enormously reduced if this distance is very small. So then we have the option that we don't have to allow for very large distances, like now 10 meters. And so your eye is a perfect tool to use for that, because you have a lens in your eye. That's the whole idea. And so now I want you to get your gratings out, and I want you to hold the gratings in front of your eyes and manipulate the gratings a little bit so that you get the lines vertical. And you will easily be able to do that. This is your light source. Your lines, your gratings have 1,000 lines per millimeter. That means the spacing of your grating is 1 micron. 1 micron is 10 times smaller than this number. So the angles are huge in your case. They're way larger than what we have there. I will make it completely dark, and then I want you to rotate your grating such that you get the spectra on either side, on the left and on the right. That means your grooves are then in vertical direction. And what you see now, way better than what I could show you in my previous demonstration, you see the zero order is the lamp itself. All the colors are right at the center. That's the lamp. That's your zero order maximum. And then you see, if you go to the right, you see the blue coming in beautifully first, because that's the smallest wavelength. You're going further to the right, you see the first order red. You're going further to the right, you see the...
He's just, so when you say it's further to the right, you're just changing the angle you're projecting at, as I stated before, and so now you're getting the second maxima view, you know, or the third maxima, or whatever. So as you turn it, you're just getting the picture from one of those other angles. And those are the ones that are spread based on the spectrum.
Second order blue, you go further to the right, and you see second order red. But since B is so amazingly small in your case, there may not be too many
But you'll, like I said, you can do it without a light source. You can do it with just the images in a room. You can look at the images in a room and turn your head to the film and see those things as a second order location. But you're just seeing what you're seeing. Nothing's been interfered with, because you're seeing a perfect image of what exists. So it doesn't make much sense to say, oh, it's an interference pattern, because interference implies some sort of destruction of some sort of content, and you can see everything as it is. All you're seeing is the light spread.
Maxima in the red. In fact, I will ask you on one of the homework assignments, which is the optional one, how many maxima in the red you will see. So essential here is that you see that the zero order maximum at the center is white light. And so it's not until you get to first and second order that you begin to see the colors separate. Now these gratings can be used to do atomic physics. There are atoms and molecules which emit very discrete frequencies. very discrete wavelengths. And when you look at them with a grating, you can see very distinctly where these lines fall, where these wavelengths fall. And that's the next thing that I want to do. I will show you now. I will turn off the white light source, and I will turn off...
Pointing out that stuff doesn't actually produce an even amount of light. It creates a little intense bars of light can be in that. So there's a whole bunch at one specific frequency of red, not all the frequencies of red. Red light isn't just one frequency is the point. Red light is from this number to this number, but the atoms themselves can be producing it all at one single frequency. So instead of producing red light through the whole spectrum of red, it's producing harsh lines of red, single frequencies, which makes sense that electrons would be doing that.
For you, neon. And so I want you to look now at the neon, and if you give yourself some time, you will see that the neon is not a continuous spectrum like you saw with the white light bulb, but you see very distinct locations where you see maxima. You see many in the red, and I think you see several in the orange.
So it's a good image. This is sort of demonstrating that the light is being produced by electrons. It's being produced by atoms that are under specific amounts of pressure and create specific kinds of photons. They don't create any old frequency. They're reflecting at a very specific frequency. So no matter what comes in, that's what they're going to, it also works for absorption lines. So they absorb a whole bunch of frequencies, and there's certain specific frequencies they can't absorb.
And I noticed this morning that I see two lines in the green. You have to look very carefully because these lines in the green are very faint. And so the whole purpose then is that with these gratings, you can not only find out which wavelength are emitted by these atoms and these molecules, but you can also find the relative strength. And that is, of course, entering the domain of atomic physics. And these gratings are extremely powerful to do that. And I would advise you to carry these gratings with you at least for the next few weeks. And when you're outside and you get a chance to see some bright lights out on highways or on the street, to look through the grating and see whether you can see these emission lines. Mercury, if you get mercury lamps, they are very beautiful. You see many, many different colors, very discrete frequencies, very discrete wavelengths are emitted by mercury in the same way, the same kind of physics that you see that here with neon. So now comes something that may come as a surprise to you, because now I would like to discuss with you the interference pattern if we have only one slit. We discussed two, we discussed capital N is a large number, but what now if we have only one slit? Even if you have only one slit.
So again, even if you only have one slit, like the obvious place you would start, and the place that, Newton did. So Newton covered it pretty well, Newton's rings. So instead of starting there, for some reason they start with 2 and then go to 3 and 5 and multiple, and then go back to the single slit because again they've sort of demystified or separated themselves from why it's happening, and now we're just talking about what's the effect. So you won't be puzzled by the inconsistency there exists between say, double slit, multiple slit, and then back to the single slit where now we're going to change the rules again.
There will be directions in space whereby light plus light gives darkness, and there will be directions whereby the light constructively interferes with each other. And strangely enough, this is given a different name. We call this diffraction. It's exactly the same physics. There is no difference. It should have been called interference, but it's, in the literature you will see it under the name diffraction.
So I get comments now and then again with people that keep pretending that the single slit is different than the double slit in its basic function, and here he's basically saying no, it's interference. It's interference. I say it's wrong to say it's interference. I'd say it's right to say it's all being caused by the same mechanical effect.
It all comes down again to Huygens' principle.
And my statement would be no, it all comes down to surfaces, and the fact that surfaces create complex pieces of the universe, and those complex pieces of the universe have electrons in them that are going to be in different states depending on how the proximity of the material objects they're connected to. And as you bring the material objects closer and closer together, you affect those electrons, and by affecting those electrons, you affect how they deflect the light.
So let me here now have a single opening, and this opening is a slit perpendicular to the blackboard, and the opening is A in size, a single one. And the plane waves come in, and Mr.
Let's understand, when the experiment's done, they don't use plane waves coming in. They usually use another aperture and then send the light to the slits. So whether it's double slits, that's how it was traditionally done. So this idea of using plane waves isn't even consistent with Young or Newton or anybody else who ever did the experiment prior to the invention of laser beams. Everybody who did the experiment prior to laser beams did it by putting the light first through a small aperture, bowing the light. So it was never plane waves that were going into the experiment. So it's just a for their own convenience they're doing that, and it's not consistent with the fact that the effect is the same whether you put bowed light in or you put straight waves in. The effect is the same. This isn't about some special circumstance that's causing the waves to curl. They were already doing that.
Huygens says that all these
They're not waves.
sources here are all going to be emitting the light at the same frequency, the same wavelength, and they will all be in phase with each other.
All right. So he's basically just saying the light goes into towards the slit, and the single photon turns into an infinite number of point sources of energy. So that's what he wants you to believe is the truth. He thinks that's got a realistic chance at being a proper definition of what's happening. An infinite number of little waves are being created. That's their theory. So I'm just saying, on its face, it should be not acceptable as an answer because it says infinite. Infinite in a confined space is illogical.
Because these plane waves arrive here all at the same time. And so I could now ask myself the question, at what angle of theta will I see maximum?
So he just arbitrarily plows a line through the middle, saying, I'm going to make two out of this. Even though it's a one slit, and it would just make one big bow, all the little tiny waves. So say if you say there was an infinite number of little lumpy waves there, all they would do is duplicate what came in, and you just end up with a wave. So I mean, it doesn't make any sense logically anyway. There's no reason for it to bow, and they're just trying to make this metaphorical to the water wave, where you can understand why the slits have an effect on water, because the water sticks to the surfaces. So there's drag, and so the drag takes the flat wave coming in, and the drag is what's bending the wave to come out. It's slowing the water down here, and this water's still going fast, and all the water molecules are tied to each other. They have adhesion, so they're dragging the slow ones with them. And that's we understand why it happens in water. There's no understanding of why light would do anything like that. Light would have friction. No reason to believe that.
Angle of theta will I see minimum, and you can also put a screen then at large distance L. You can call x equals 0 here, and you can ask yourself, where will I see these maxima and where will I see these minima? To derive this, in this case, it's not easy. Again, I refer to 803. It's as difficult as deriving, in this case, this whole structure in between the maxima. One thing is obvious, and that is...
I've seen 803. I don't think he does a proper derivation, in the sense he doesn't really get the two-slit pattern with the superimposed pattern, so he doesn't derive that at all. And in the case of the single slit, again, the assumption is a bunch of assumptions about a bunch of cancellations and a bunch of other stuff, and I would argue that it still doesn't describe the actual pattern, and the actual pattern is a bunch of bars, and it's not a gradual wave. So the derivation doesn't match what you actually see on the wall.
That you've got to get a maximum that is non-negotiable when theta equals 0. That's simply a matter of symmetry of the problem. If all these sources are in phase, clearly you're going to get a maximum here. No one will question that. The minima is very tricky. And the minima will fall the following locations.
So now how they change it is now when they use the n number. See, they're going to get rid of that 0. And the way they're going to do it is the n number now is going to represent where the minima are. So where n before was where the light hit, now the n number is going to be where there's no light. So that's how they pervert the math to try to make it work.
Sine of theta of n equals n times lambda divided by a. And for small angle approximation, this is the same as theta n in radians. And when you see that equation, your first reaction should be that maybe I goofed by a factor of 2. Because your first reaction will be, that's the same equation that we have there, and then we have a d there. And so how can we have minimum here where we have maxima there? Well, the situation is different. The best way that you can see that that equation is not wrong is perhaps the following. Suppose you take the angle theta 1.
The simplest way to understand it is, with the single slit, there's so much light going through the middle that it washes out the first maxima. So there's actually a maxima, there's actually a minima in the middle and 2 maximas. And so you actually have 2 bars plus the dark bar in between. You can't see the dark bar in between because it's been washed out by the light that goes straight through. So you don't see it. But that's what happened. So you really do have a 0 in the middle, then 2 bars, then zeros, then bars, then zeros, then bars, then zeros. So the middle is essentially 3 bars worth, 3 on-offs, instead of what you would traditionally have, just 1 and then 2 and then 2 and 2 and 2. So it starts off with an odd number. That's why they have to invert their numbering sequence, because it's got an odd number.
So that's for n equals 1. Then the relation that you see there will tell you that this source here, this Huygens source, and this Huygens source have a difference in path length of lambda. And so you will then say, aha, that's constructive interference. That's true. But that means this Huygens source and this Huygens source.
Right. So he arbitrarily now compares it to the middle one. And so that's how they create 2 waves. So he just you can see 3 dots now. He's basically just saying, okay, now I've just created 2 waves, really. Because I've split the single slit into 2 slits by just arbitrarily deciding to compare the edge to the middle. So it's just this deception that instead of overtly saying, I'm going to make 2 waves out of this, even though logically you can say there's only 1 wave, I'm going to make 2. And I'm just going to do it. And I'm not going to do it for any logical reason, except I need to, because I can't explain what light's doing without creating 2 waves.
We'll then have a difference in path of half a lambda, so they will kill each other. And that means this Huygens source and this Huygens source will have a difference in path length of 1/2 lambda, so they will also kill each other. And so in this upper half, there's always one Huygens source which will kill the one at the bottom. And you can do a similar reasoning for the angle theta 2. And so that is indeed...
Yes, and you could do that trick with anything, where you create an arbitrary middle, you'll always end up with a remainder, So, I mean, you can do that with anything. But there's absolutely no reason to create that middle one and say, I'm going to compare this middle one to all these others, because there's not necessarily even a middle spot, right? The middle spot could be an opening, could be a non-wave, could be where 2 lumped waves meet. So there might not even be a middle. Or it could be a wave in the middle, and then you have to cut the wave in half. So, there's no logic defending it. It's just something they do to pretend there's 2 waves.
The correct equation, you will find complete minima when theta 1, in terms of radians, is lambda divided by a, and theta 2 is 2 lambda divided by a, and so on. That's where you find your minima. And if you convert that into x, where they actually fall on the screen, well, then x1 will be, for small angle approximations, L times lambda divided by a. That's no different. And so now what I owe you is a pattern. What will the pattern look like? When I look on the screen there, what will I really see? Well, it's going
So this is another one of the big deceptions. He's going to draw the dullest pattern possible. And, you open the slit a little bit, you get 50 bars. He's going to draw it like, oh yeah, there's just one big lump in the middle and there's little ones.
To look very different from what you may think. I will plot it now in terms of x. I could have plotted it in terms of theta, but I decided to plot it in terms of x. So here, at x equals 0, there is unmistakable, unnegotiable, there is a maximum. That is...
It's actually two maxima, okay, with a nothing, a minima in between. So that's what you're going to get in the middle. It's wider for that very reason, is that it's two maximas and one minima.
That coincides with theta equals 0. And then here, at lambda divided by a, completely destructive interference. That's that angle theta 1 times L. And then here, L 2 lambda divided by a, complete destructive interference. And this
so again, they've changed the numbering sequence from now where the bright spots are to where the dark spots are. So again, just another reworking of the mathematics to try to attempt to say this is the same formula, we're using it for all these slits, and it's really not the same formula at all, because what the variables represent isn't the same.
Same is true, of course, on the other side. And what you're going to see now in terms of the intensity that I showed you there, watts per square meters, is a curve that looks like this. You have an enormously broad maximum, absolutely 0 here, very small maximum, absolutely 0 there, very small maximum, and 0 there, and this continues for a long time.
So again, not representative of the real pattern at all, beside the fact that yes, the center dot's going to be very bright, but the other bars can be also very bright.
And this is very different from anything we've seen with multiple sources.
So again, nothing different at all if you do it at the proper width. They're making the width deliberately narrow here, and so it's not a fair comparison between the experiments. If you have the width of the slit the same width as the total width of the two slit in the single slit, you'll get lots and lots of bars.
Intensity here is I0, then the maximum here, which I didn't even calculate where it is somewhere in between these two minima, but I didn't calculate precisely where it is. That maximum is very low. It's only 4.5% in strength of I0. And this is even lower. This is only 1.6% of I0.
All right, and you won't see that being consistent for wider. You widen the slit, and those numbers change dramatically. I mean, this is huge. 4.5% is tiny. But again, if you actually do the experiment, you're not going to get any kind of proportions like that.
So when you look at a diffraction pattern, we call this a diffraction pattern like this, you will see a very broad center maximum, and then you see these dark spots on either side.
And that's just not the truth. It's not very broad. It's just two maxima and one minima. So it's 3 units wide. That's the center. And then everything else is the regular on, off, on, off, on, off. So technically it's only 1 unit wider than the other units of on-off, the other pairs of on-off, on-off.
And you see light coming up again in between them, sort of sub-maxima. And so the width of this center maximum, this width, which is really x1, that width is then L lambda divided by A. And if you want to be picky and you say, well, the center maximum is really twice that much, fine, be my guest. But this is clearly a measure for how wide that center spot will be when you see it on a screen.
So it's not, he said whatever, twice or whatever. No, it's just 3 units. It's one, you can't see the minima that's right in the middle, but it's just 2 maximas and a minima.
And now there comes something that is completely non-intuitive for you as well as for me. And that is, if you make A very small, that means you let the light go through an extremely narrow slit. Then this, what you will see on the wall, is extremely wide. The smaller A is, the wider it will be.
The wider all of the bars will be. So all of them get wider. So the little ones get wider, the big one gets wider, everything gets bigger, because you're changing the angle that the theta angle changes dramatically as you make the slit narrower, which just means if, say, the photons were hitting electrons, you're going to understand the electrons are getting more and more tense because they're feeling the pressure from each other, and that higher tension means they're bending the light more.
Exactly opposed to what you would predict. You would think if you make the opening through which you put light very small, you would think that what you see on the screen is also very small. It's exactly the opposite. And this is what I want to demonstrate to you. I have here a demonstration in which a variable slit, I can vary A, and we will use the brightest laser that we have, a beam of green laser light, or 5,400 angstroms. And what I will do is, I will make this opening narrower and narrower and narrower. And as I make the opening, I start very large. I start with a large opening of maybe 5 millimeters. And the large opening, A is so large that this is negligibly small. Because A is very large, then this is not very large, this is very small. But as I make A smaller and smaller and smaller and smaller, there comes a time that the diffraction width is going to be dominating the whole scene. And what you will see then on the screen there, that the bright spot will get wider, 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 wider.
Right, and the irony is there's no description of what when he has it wide and he has lots of bars and they're all kind of evenly bright. There's no explanation there's no mathematics illustrating that. I mean, you're certainly not going to have these dramatic changes in intensity from 4.5% to 1.6%. I mean, that's 1/3 as bright. It's dropping by 1/3. You're not going to see that anywhere.
And that for me is always so enormously fascinating because it goes so strongly against our intuition. And so this is what I have next on the menu. I have here this variable slit. I must make sure that I have my flashlight, and I'll turn on this laser that I earlier accidentally turned on. I hope it's coming on. Yes, it is. And so you see there, the slit is now very wide. And so the size of that slit that you see there, the size of the bright spot, is now entirely dictated by the divergence of my laser beam. The diffraction width is negligibly small because A is very large. But now watch. Now I'm going to tighten, make A smaller.
So you do have diffraction right there from the aperture that the light's shooting through the laser. And you have the little star pattern, which is essentially the same effect that he's now going to put another effect on.
I'm doing that now. I'm making it smaller and smaller. The diffraction which is still negligible. Making it smaller. Ah! I'm beginning to see the dark lines. Ah!
Yeah, so a ton of lines, and like I said, you can do it with even more lines. So, you know, the fact that his is still very intense might just be because of the intensity of the laser he's using.
Diffraction which is taking over.
All right, and yeah, I don't, you know, obviously you can get a lot more pattern out of a single slit than that.
Look at the center maximum, right there. It's getting wider, it's getting wider, and I make the slit narrower, it's getting wider.
And the key thing is that you have lost the stuff going up. So remember the little star thing that you had before, you've lost that. So there's not sufficient enough light going through to create any a visible diffraction in the other directions from the laser, which is sort of interesting. I mean, there's no explanation for all these little artifacts. So why is narrowing the slit this way changing the diffraction that was going this way? And part of that just might be because you have narrowed the slit. You've evacuated the electrons that were affecting that before. So those electrons were also affected. The ones top to bottom are also affected when you narrow it this way. You're messing up the electrons on the other two surfaces.
It's getting wider, and look how beautiful you see these destructive interferences, where light plus light gives darkness. Wider.
So there's no light plus light creates darkness. All the photons, no photon is destroyed by this experiment. They all go to a different location. So unlike in water waves and all that stuff where there's two forces that consume each other, nothing gets consumed, no energy gets consumed, and all the photons get to the wall. They just get there in a different location. So they're moved to a different location. It's not like water waves at all.
Wider. Right now it is at least 10 times wider than it was before. Now it is 20 times wider. And it gets very faint. Of course it gets very faint, because if I make the slit very narrow, not much light goes through. There's nothing I can do about it. But notice how incredibly impressive this is. How white that center maximum becomes. And that is very characteristic for diffraction. The narrower the slit, the wider the diffraction pattern at the center maximum.
And wider the interference pattern, as he stated earlier. Diffraction is just interference. But again, I would argue it's not interference. It's the fact that as you narrow the slit, You evacuate the electrons, you change their disposition, and that's why you've lost all the stuff that was going up and down. The up and down stuff shouldn't have been disturbed, correct? I mean, logically, it was doing a certain thing. So why doesn't the light that's going up and the light that was going down, why isn't it still doing what it was doing?
Now, this is in monochromatic light. Monochromatic light means that you have practically only one wavelength. And there is a way that I can make you see this from your own seats. And that is what we're going to do with the cards that you have. So if you can get the cards out now. We did this in one color, right? In green lights. Almost one color, almost monochromatic. So you see a beautiful pattern here. Very well-defined dark lines. You now can use this little slit that you have, put it in front of your eye, and I'm going to make you see this white light. And you would see all the features that you were supposed to see, but it's even more interesting in white light, because with white light, you have a little red, you have a little blue, you have a little yellow, and so these minima will fall at different locations, of course. And so you don't see it as beautiful as I showed you, as distinct as I showed you in green. But
so this gets back to the Young thing. Young did it with, sunlight, and it got little balls of different colors, almost representing the sun.
But you see very distinctly the center maximum, and you see the dark lines on either side. But the main reason why I want you to see this is that if you manage to manipulate the size of the slit, the size of A, if you manage to manipulate that, when you make it narrower, notice that the diffraction pattern gets broader and not the other way around. So first make sure that you get it, that you begin to see the dark areas, and then try to make it a little narrower, and then you see that it opens up. This is precisely what I did with the variable slit here. So give it a bit of time. What helps me that actually you don't have to pull it open, but that you can move one piece of the card behind the other card. So your one thumb goes to the back and your thumb comes forward. That works very well for me. Who can see clearly the diffraction pattern? Unmistakably. Very good. Take the card with you, impress your parents, and look at home at very bright street lights, and you will still see the same diffraction pattern. Although not as ideal as you see it here, because our source is a line source, and that helps, of course, if your slit is vertical.
So again, he's artificially creating a vertical light so he can create bars, to imitate,
Okay. If I don't have a slit as an opening, but if I have a circular opening, then the pattern that you would expect is the same that you see here, but you have to rotate it about this line because you don't have axial symmetry. So you don't have a long slit, but you have a circular opening. And indeed, that is approximately correct. If you had a circular opening, you would see a center maximum, which would be very bright, and then you would see rings around it of zeros. And so if I try to make you see it, this would be the center maximum. There would be a ring around it here. Complete darkness, and then again a little bit of light.
Right, so it's just Newton's ring. So all this slit stuff is just duplicating what Newton did 300 and whatever years ago. And so it's a very old effect. It wasn't Young, didn't do anything miraculous in bringing up the subject again. And then again, they didn't, from 01 to 1930, they couldn't come up with an explanation. So they were... And then they started doing all this Einstein stuff, and then they invented this quantum mechanics crap, and then just decided they're going to make photons into waves, and they went with the Huygens explanation. But, it's hundreds of years of not having enough evidence to do that, and then all of a sudden they just decided, hell with the evidence. We'll just make a declaration.
Not very much, because remember that this maximum is only 4.5% of that one, and then you would see again a ring with complete darkness, and so on.
So again, that 4% number just has to do with how small you make the aperture. You make the aperture bigger, that 4% number just disappears as being relevant.
So you have a little pinhole, and this is the image that you would get on a screen from that pinhole. And you would think now that this angle, from here to here, this is theta equals 0, and we call that theta 1. This is the theta 1 where you see your first 0, You would think that that is lambda divided by A if A is the diameter of your pinhole. Well, it's almost that. It is a little larger because a pinhole, the circular geometry is different from a line. And so take my word for it that it comes not at lambda divided by A, but it comes at roughly 1.2 lambda divided by A. If you want to be picky, it's really 1.22 times lambda divided by A. And this, of course, is in radians again. I work now exclusively in terms of radians, small angle approximation. And so this raises the issue of what we call in physics angular resolution. Suppose I have a pinhole, and I look at the images of two light sources. One light comes in from there, and the other comes in from there. Could be the headlights of a car, could be two stars in the sky.
All right, so I don't know if there's a real connection between these two subjects, but anyway, it's interesting. Yeah, so instead of really going into detail about that circular thing, why a circle makes a difference, because of the averaging, I guess, of the amount of light you're actually going to be able to see. So where you'll see it isn't necessarily where it starts and ends, because it has to average over the circumference of a circle versus a straight line, which is, straight lines all do it in one place, circles have an arc, and so it has to be an average through that arc.
Sky. Well, each one of them will give a diffraction pattern. That's non-negotiable. You can never bypass diffraction. So one star will give a diffraction pattern here, or one headlight, and the other will give a diffraction pattern here. You would have no problem to say, oh yeah, there are two light sources. There's one star, and there's another star. Okay. Now make the angle between the two sources smaller and smaller and smaller and smaller, so that these two diffraction patterns come closer and closer and closer and closer. How close can you now bring them so that we, you and I, will still say, yeah, there's still two sources. We call that angular resolution. And so how we define angular resolution is that both light sources have exactly the same strength, and let's assume for now, for simplicity, that they're monochromatic, so that there's only one wavelength that they emit. Then the criterion that is generally accepted, so that we can still decide that there are two light sources, that this one, the center of this one, is no closer than the location where this one has complete darkness. In other words, the spot of the second star should fall right where the other one has darkness. If you bring them closer, your brains will say, no, 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 that's not two sources, that's really only one source. And we call this the Rayleigh criterion of resolution. And that Rayleigh criterion of resolution, therefore, is...
And I think this is a lens effect, not a pixel effect. So even if you increase this major pixels twice as smaller on your screen you're looking at, you'd still be stuck with the same problem, because this is a problem of the lens itself.
That the separation between the two light beams, stars, or the headlights from a car, the separation has to be larger than this angle. And it is a function of A. If A is larger, then that angle can be substantially smaller. And this is what we call the diffraction limitation on angular resolution. It doesn't matter whether you have a pinhole, or whether you have a lens, circular lens that we use with telescopes, or whether you have concave mirrors, which we use with telescopes. In all cases, are you always stuck with the idea, at best, that's the best you can ever do, that is the angular separation, that theta, I call it here the theta 1, is that 1.2 lambda divided by A, and that is then in radians. If you take a lens which has a diameter A of about 20 centimeters, then that translates into a theta 1 of about half an arc second for 5,000 angstroms. So I take lambda 5,000 angstroms. Remember, an angstrom is 10 to the minus 10 meters. So theta 1 then becomes half an arc second, 0.5 arc seconds. An arc minute is 1/60th of an arc degree, and an arc second is 60 times lower than that.
So the bigger you make the lens, the less this effect will ruin you. And the smaller the lens, the more it ruins you.
And so if A were 2.4 meters telescope, 2.4 meter telescope, that's a real biggie, then theta 1 would be approximately 1/25th of an arc second. So the larger you make your telescope, the better angular resolution you would have.
But then the problem's going to be is everything's jiggling a little bit through the atmosphere, so that ruins you. So even if you get to a big telescope, you're still screwed, because the amount of movement of the objects you're actually looking at is so big that you can't get any finer.
This angular resolution is 12 times better than this one, because A is 12 times larger. in both cases and in what follows, I have ignored the factor 1.2. So now you may think that if you take a 2.4 meter telescope on the ground and you look at stars, that two stars equally bright, you will be able to tell them apart if they are farther away from each other than 1/25th of an arcsecond. That is not true. The contrary, it is very bad. You can't even tell them apart often when they are half a second apart. And the reason for that is not that the diffraction limitation is going to kill you, but the reason is that the air is always turbulent. And it is the turbulence on the air that makes the image, the diffraction limited image, which itself is very small, move around on your photographic plates. It moves it around in a matter of 10 seconds over an area which itself could be as large as 1 second. Astronomers call that seeing. And so when you look at your picture, the whole star is smeared out over an area which is in angular size 1 arcsecond, or maybe half an arcsecond at best. So you can never achieve this from the ground.
Right, and so this brings up the Eddington experiment, obviously. So taking the star field, bouncing it off a mirror into a 12-inch telescope, you know, and having some hope over a 15-second time exposure of, yes, not getting stuff moving all over the place, and trying to say where the exact location of stars are when they're on the piece of paper, they're little blobs of streak.
So all telescopes from the ground, without exception, can do at best half an arcsecond. They cannot do much better because of the air turbulence. And this is now the great thing about the Hubble Space Telescope. Hubble is up there, or maybe down there, whichever it is. I don't know where it is. Maybe Jeffrey knows where it is, but it is somewhere. And Hubble has no air. And so Hubble doesn't suffer of the air turbulence. And so Hubble's mirrors are indeed diffraction limited. And Hubble has a mirror which is 2.4 meter diameter. And indeed, at 5,000 angstrom, I checked that yesterday with people at Hubble Space Telescope, indeed, Hubble is diffraction limited, and Hubble has an angular resolution at 5,000 angstroms, which is about 1/25th of an arcsecond. And at shorter wavelengths, it's even better, and at longer wavelengths, it is a little worse.
So for some reason he said he is ignoring the 1.2 thing, which is kind of funny, because so apparently it's a little less than that because of the 1.2 thing that he is ignoring. I don't know.
And so I would like to show you at least one picture of Hubble without going into the details of what you were seeing of the astronomy. And that's the one that is coming up. It's a very famous picture that Hubble made several years ago. Here's a picture of a supernova explosion. John, if we can have the slide. There it is. You're looking here at an explosion. It's called supernova 1987A, which occurred in February in 1987. This object is 150,000 light years away from us. That means the explosion really took place 150,000 years ago, but we saw it for the first time in February 87. And without going into the details of what you are looking at, which is of course very fascinating, but that's not the objective today, I want you to appreciate that this distance here is 1 arcsecond. And look at the incredible detail that Hubble can show you. If you took a picture like this with a ground-based observatory, this whole part would just be one smudge. You would not be able to resolve that. And that is the power that you see in front of you now of a diffraction-limited telescope, which has a diameter of 2.4 meters.
Yeah, so he doesn't want to explain what we're seeing here, but I guess the other images, the red images, the circles, are artifacts, but who knows? Lens artifacts.
You get an angular resolution which is very close to 400ths of an arcsecond. The amount of detail that you see is incredible. That's the big power, the big reason why this telescope was put in orbit, to do away with the air turbulence, what the astronomers call as seeing, which is always a limitation of your angular resolution. So in the remaining 5 minutes, I want to address the issue of the angular resolution of your own eye. You can now calculate what the ultimate angular resolution is of your own eye, because you can estimate what the diameter is of the pupil, the opening of your eye. 3 millimeters, maybe 5 millimeters, a little bit larger at night when it is dark. Pupil opens up, but we can calculate what this is. If I take 4 millimeters, so I put in for A 4 millimeters, and if I take lambda 5,000 angstroms, it's not an unreasonable value, then I find that the best angular resolution of a human eye is half an arc minute. Cannot be any better. There's no way around it. You're always stuck with the diffraction limitation. I think...
So compared to an arc second to an arc minute, 60 times, you know, so it's 60 times worse at differentiating objects at a great distance than, say, a telescope.
So that most of you will not be able to see with an angular resolution of 1/2 arc minute. Most of you are probably in the domain of 1 arc minute. It's a little larger than diffraction limited, but it's very close to that. And that is something that I would like to test, not to see how good your eyes are, but for yourself, to get a feeling for angular resolution. And the way I'm going to do that is as follows. We have prepared a box which Marcos is going to wheel in very shortly, which has 2 pinholes at the top, and these 2 pinholes are 2.5 millimeters apart, and then there are 2 pinholes which are 5 millimeters apart, and then there are 2 pinholes which are 10 millimeters apart, and then there are 2 pinholes which are 15 millimeters apart. So maybe we can take a look at that. There it comes, thank you Marcos. Here are 2 pinholes which are 2.5 millimeters apart. We repeat the whole thing 3 times. And the reason why we do that is so that the different angles in the audience, you can probably always see 2 pinholes well. What am I going to do now to test the angular resolution of your eyes? If I make the assumption that your angular resolution is 1 arc minute, no worse, no better. Remember, it can never be better than 1/2 an arc minute. That's non-negotiable, but it could be worse than 1 arc minute. That would mean that all students who are closer than 9 meters from me should be able to see this as 2 independent light sources. Those who are farther than 9 meters away from me will not see these as 2 sources. If they did, their angular resolution would be better than 1 arc minute. And all students which are closer than 17 meters will be able to say, yeah, I see these as 2 sources. And all students which are closer than 34 meters should be able to say, yeah, I see these as 2 sources. And so we're now going to make it a little darker, and you don't need your gratings, you don't need this card. I just want you to look at the lights, these light sources, and then tell me which you're going to see as 2 separate light sources. And that then allows me to tell you very roughly what your angular resolution is. So try to look at them.
So obviously the camera has very good seeing. So, you know, it doesn't have the, it's 60 times better than we are almost, whatever the number, 50 times, 40.
And so now my first question is, who can see the upper, either here or there, they are the same, who can clearly see those as 2 light sources? Come on. Come on! You don't see them as 2? Is something wrong? Is the lights not on? You must be kidding. Are all of you sick or something? Oh man, I have no difficulties at all. The upper one is 2 light sources. You all got to see an eye doctor. Okay, who sees the second line as 2? Who sees the third line as 2, but not the second? You see how interesting? Just look around you. You see we're moving back in the audience. Who can see none of them as 2 light sources? Okay, so maybe not. No eye doctors are needed then. Who can only see the third line as 2 sources? Only the third line. Okay, well I expect that. So, yeah, maybe your angular resolution is not very good. Do you wear glasses? So I'm asking you. So you see the third line as double, and not the second line. No, there's nothing to worry about, maybe 2 arc minute resolution. So now you have tested your angular resolution. When you think of diffraction, it's really an incredibly
okay, we're almost done.
Fascinating thing. Because what does diffraction actually means? That it is a limitation that is put upon us, on everyone, also God. No one can bypass diffraction. No matter how hard we try, we can never undo our chains and handcuffs that are imposed upon us by diffraction. And remember, it's all Huygens' fault. But let's forgive Huygens, because after all, he was Dutch.
Right. So again, it doesn't have anything to do with Huygens. It has to do with electrons. Photons hit electrons. That's what they do. That's what all the evidence, the volume, 99.99% of the evidence indicates that photons hit electrons. That's what they interact with. And I would argue that instead of believing in this wavy, don't interfere with anything but empty space itself, somehow photons are being broken, and photons are big long things that go across big wide slits and split in 2 and do all kinds of wacky stuff. Instead of believing that, just understand that surfaces are complex things, and you're sending a photon through a complex field, and the smaller the slit, the more likely you're going to be sending the photon through the complex field, and that complex field has electrons in it, and the photon hits the electrons and does what photons do when they hit electrons, which is often scatter at specific angles. So Good. Got it done. Sorry for the long video, but, you know, it's in one piece. So it's probably more economical in some respects. And I'm still not quite in the frame, but it's good enough. Working on it. Going to be changing things. Got a new monitor. Big $50 used one. Really nice. Anyway, so I have to take my desk apart. Anyway. So, till next time. Such.